Swayam Prabha. Digital India. Educated India.
Hello, welcome to the course on transport phenomena. This is lecture 22. So we will be discussing natural convection today. So far, in the convection we have discussed about external force convection, internal force convection, in general convection methodology, and as you will see in the pattern over here is that we analyze first the heat transfer aspects, and then main problem is actually to find how do you find the convection heat transfer coefficient, and that is typically done through correlations, and sometimes it's numerically developed, but very often it is these are empirical equations, and as you know, as an engineer we should be aware what are the correlations available, and how we can use it under what conditions, because the correlations are developed under certain conditions. As you would have seen in the previous lecture, we talked about some correlations that are developed only for Prandtl number, let's say less than 5 or maybe greater than 5, or for liquid metals where Prandtl number is much smaller. So you can use only under those circumstances. In addition, also you have to be aware of the flow behavior. Sometimes some correlations you can only use for laminar flow, some correlations you may use for turbulent flow, and so on. Other aspect is of course on this convection heat transfer coefficient is very often we want to know the average convection heat transfer coefficient, and because of this boundary layer development, we have seen that the convection heat transfer coefficient varies significantly with a spatial coordinate. So you should be aware, which correlations are available for average heat transfer coefficients. Sometimes you may be able to calculate average heat transfer coefficients as well if equations for local heat transfer coefficients are available. This was just a short summary on what kind sort of methodology or what's the content we have discussed in convection heat transfer. So far our discussions have been limited to forced convection, where you have an external medium, external equipment. For example, you can have a fan, a blower, or pump that you can use to have the force velocity of fluid, and that gives you very high heat transfer coefficient. In contrast to that, you can also have natural convection, and that is what we are going to discuss today. In this case, you don't have any such equipment as fan or blower or pump, but because the density is temperature dependent, so if you have a lighter fluid above if you have higher temperature in the bottom, let us say, and lower temperature on the top, then you would see that because the density of this fluid is smaller than this one, so it will move up and this will move down. So you will have this kind of movement, and we are going to discuss in detail. One common example, if you leave a glass of milk to cool, by putting in ice bath or even in water, you would often realize that the milk at the bottom is colder. Okay, because of this natural convection as well. Okay, so let me share this and we get started. So we are on lecture 22. So today we'll talk about natural convection. We'll discuss the physical mechanism behind this natural convection, and then we'll talk about similarity parameters. So as we have been discussing in general in transport phenomena, you will see that you will always have some new dimensionless number that comes into picture, and that is actually linked to the physical mechanism of the process. So here you will also again see few more dimensionless numbers that will derive through similarity parameters, or not by non-dimensionalizing our flow and heat equation. Then we'll look at some specific cases: vertical surface, horizontal cylinder, and sphere. Let's move on. So as I was saying, natural convection essentially means the convection without forced velocity. So we do not have any fan or blower or pump in these cases. So what happens is essentially you have density gradients, because you have density gradients, and because of that density gradients, you will have buoyancy forces. You have density gradients, of course, because of your temperature gradient. Okay. So generally, when we talk about natural convection, the thought comes that it's kind of weak and it's nothing compared to forced convection. So can we just ignore it? The short answer is no. You cannot ignore the natural convection, because very often natural convection actually, if you're talking about insulation, etc., then natural convection is what actually provides the largest thermal resistance. That is one, because of thermal resistance region. So it provides largest thermal resistance. So if you ignore that, then you will overestimate the heat transfer. And of course, in devices such as your smartphones and things like that, where you cannot have moving part like a fan, you are actually relying on natural convection for the cooling. Operating temperature of machinery. So very often machineries heat up, and sometimes you have cooling provision. You can have the machines could be cooled by water or things like that. But very often you don't have the you rely on natural convection. That is natural convection of air for your machines to be cooled. So depending on how much power you can have in the machine, it actually is limited by how much surface temperature could be maintained due to heat transfer to natural convection. Natural convection also determines temperature distribution in the building. So sometimes you do have ducts and all those things, but very often your walls, etc. Natural convection is important. Pollution in cities. Pollution actually temperature gradient affects the air flow as well, and that can affect how long your pollutant particles can be remain suspended in fluid in air, and that's what gives you this PM 2.5 level or PM 10 level and things like that. So natural convection is ubiquitous. You find it everywhere, and although the heat transfer coefficient itself is much smaller than forced convection, but you cannot ignore it. We have to consider it in many cases, and we'll discuss under what specific circumstances we must consider it, and in what specific circumstances your forced convection could be much higher. So we'll discuss all that. Okay, so typically, as we have said, for in general, density of fluid decreases as temperature increases. Okay. Of course, there could be cases, for example, maybe water, where some anomalous behavior is there, but generally, the density, as your temperature increases, your density decreases. Okay. But density gradient does not necessarily mean free convection. You should be aware of that. So let us say if you have two plates in which let us say the one temperature is T1 and this temperature is T2. So if T1 is greater than T2, then rho or if you look at rho, here will be low, here it will be high. So you have you have density gradient. But since this lighter fluid is already on top, so it's kind of a stable, and you will not have any flow, so you will not have any free convection. However, if you're on the other side of it, in which T1 is less than T2, that would mean that you have lighter fluid here, and you have heavy fluid here. So then this will go up, and then this will come down. So you will have this kind of circulation. Okay. Then the other distinction is free boundary layer flow versus flows bounded by surface. What do we mean by free boundary layer flow is, let us say if you have a rod, something like this, very thin rod, which is heated up. Now, if you just look at the cross section, it will what will happen is what we call is it will form a plume. here it is hot, ambient fluid is cold, so it will heat up and rise up, and again you will have boundary layer formation, and then it will go up and then it will form plume. So if you look at the area over here, if you just ignore that, then whatever is the plume is forming, then that is there is no for the part of the plume, it is sort of free boundary layer flow. Okay, similar thing could happen if you have a jet, let's say jet that and hot fluid comes out, so it will just go up. So if you look at this part, there is no boundary layer. This is in contrast to, let us say, a flow that is bound by surface, which could be, this is free. Now, if you look at this one, then you have, let us say, if you have a hot vertical plate, and then you will have some kind of flow, and then because there will be natural convection, because your if Ts is greater than T infinity, then here you will have lighter air will go up, and then you will have boundary layer formation, etc. So in this case, the flow is bounded by the surface. So this is another distinction you should recognize. Okay. So we'll closely look at this specific case called heated vertical plate. In this case, what will happen? We'll first, let us see. You have this plate, which is at Ts temperature, which is greater than T infinity. So what will happen is, the fluid here, fluid close to this surface will heat up. Fluid close to this surface will heat up, and that's why your fluid will come, and then it will rise up. It will rise up, and as it is moving up, it will actually entrain the surrounding fluid. Entrainment happens. Basically you increase the velocity, so pressure drops, so you will have more entrainment, right? Because of that entrainment effect, you will have a boundary layer development. Okay. Now the nature of this boundary layer is different. The way we have been defining boundary layer is that the velocity, over here it should be, as v infinity. In this case, there is not, it should be almost equal to 0. What we are saying is that there should not be relative velocity between this and this, right? Just at the boundary. Since this is 0, so this has to be 0. So if we are looking at the velocity profile, it has to be 0 here. And here it has to be 0 because of no slip condition, right? Here also 0 because your relative velocity is 0. Here 0 because of no slip condition, right? So velocity profile will look something like this. Right? It's kind of bell shape. Okay, so this is in contrast to our typical velocity profile, where here it will be 0, and then here it will go to v infinity and so on. Okay, so you should recognize this again. It will go through maximum, then it will come down, and the boundary layer development in this case happen because of entrainment effect as well. Okay, so now if you look at the temperature profile, of course, temperature over here will be larger, and then it will go down. So thermal boundary layer will be like this. So if this is your, so this is your Ts. Okay, so this is your delta T thermal boundary layer. This is your hydrodynamic or velocity boundary layer. Okay. Yeah. So we discussed velocity 0 is 0 for y equals 0 and y equals infinity. So this is our x-axis, x, and this is y. Okay. So we also saw the thermal boundary layer formation. This is your velocity boundary layer. This is your thermal boundary layer. Okay. So now we want to look at this property. You must be aware of volumetric thermal expansion coefficient, which is defined as if you call it beta, is defined as the way density vary with temperature. Okay, it should be dou rho by dou t. Okay, so we can if you write in approximate form, then you will see that beta can be written as -1 by rho delta rho by delta t. Okay, and where delta rho is defined with respect to bulk density, so rho infinity minus rho by t infinity minus t. So from this, if you rearrange, you can write rho infinity minus rho is approximately equal to rho beta t minus t infinity. So what you can see is from here you can also write delta rho by rho, and we will see why this is again important, beta t minus t. Okay, if you do the same thing for ideal gas, you can go through the steps. Beta is essentially 1 by t, because you know that Pm equals rho RT. Okay. Okay. So let's look at the governing equation for this for this case, that is heated vertical plate. So we start with continuity equation, which is dou ux by dou e by dou x, dou v by dou y. So recall that for us this Ts is greater than T infinity, and our x is in upward direction and y is in this direction. Okay, so now if we look write the x momentum equation, x momentum equation will be like this. So you will have rho u dou u by dou x plus v, and again we are talking about at steady state. So that's why you will not see the time derivative here. Dou u by dou y. This we have looked at earlier in the course, right? Minus dp infinity by dx plus rho gx plus mu. I'm going to drop the term that is with axis x, because as we have seen, the velocity gradient in this direction is much larger, so you will have more viscous dissipation in this direction compared to this x direction. So we just ignore the x term. Okay. So now what we want, we want to use the so we have said that dp infinity by dx, if you look at dp infinity by dx, dp infinity by dx is essentially minus rho g, rho infinity g, because g is again your downward, so even gx should be equal to minus g. Okay, so if you substitute this thing here, let us just look at these two terms first, and then we'll come back and write. Okay, so we are just concerned about minus dp infinity by dx, so minus dp infinity by dx plus rho gx. So gx will be minus g, that we have said. So this will be minus plus, so this you will have rho infinity g. Okay, and rho infinity g. Let's also divide everything by mu. So everything by this rho. If you do that, then you will have minus 1 by rho here, and then this rho will cancel out. Then this will be mu by rho, which is again momentum diffusivity, that is nu. Okay, so rho infinity g by rho from there. This is 1 by times 1 by rho. Yeah. Minus rho will cancel out, so you will have minus g. So this will be equal to g rho infinity minus rho by rho, which we know from here. Delta rho by rho is beta t minus t infinity. So it will be g beta t minus t infinity. Okay. So based on this, what we can write is essentially this left hand side will be as it is. We just took the rho on the right hand side. So this will be dou u by dou x plus v dou u, where u and v of course are x and y component of velocities, dou u by dou y, that is then this is equal to your these two terms, which is equal to g beta t minus t infinity. Okay, g beta t minus t infinity. And then the last term will be essentially nu, because we had mu by rho is nu, which is momentum diffusivity. So this is dou to u by dou y square. We neglected the x term. Okay. This is your momentum equation. And we have already seen the continuity. And then you will have similarly you will have energy equation, which will be again similar, u dou t by dou x plus v dou t by dou y. And then again we write the we are ignoring here the viscous dissipation term for energy balance equation. So now if you look at these two equations and along with your continuity equation, especially momentum and energy equations are now uncoupled. Sorry, it's coupled. Earlier, you know, if you had just earlier, what you could have done is you could have solved a continuity equation and momentum equation. From there, you could get the velocity profile, and then you can solve the energy equation. Now it's kind of coupled, right? So you have temperature term here and you have temperature term here as well. You cannot solve this equation without knowing the temperature, and you cannot solve this equation without knowing velocity. So these are coupled differential equations. We'll not get into the solving these differential equations. However, we'll again try to non-dimensionalize this equation and see what, you know, what kind of dimensionless parameter it gives, and so that we can find the nature of our ultimate goal is to find what does Nusselt number depend on. For external force convection, we said that this was function of Reynolds and Prandtl number, and you would have seen that most of the correlations were actually, all the correlations were actually the function of Reynolds and Prandtl number. Okay, so to non-dimensionalize, we take some similarity parameters. So we take x star is equals x by L, y star is equal to y by L. Now for the velocity, we don't have any reference velocity like in the forced convection you had a u v infinity or bulk velocity, but in this case we don't have. Let us take some arbitrary reference velocity. We'll come back to this later. You will see it's again, and then v star will be v by u naught. Okay, what else is left? U, x, v, and then you have temperature. So temperature T star we can write define, again you have a reference temperature in this case, so you can use that. Okay, so now if you do the momentum equation, if you look at this term u du, so that will give you u naught star, right? U is equal to u naught times u star, so this will give you u naught square. So we'll first do the momentum. U will be u is equal to u naught u star, so u do u will be u naught star, sorry, u naught square u star do u star, then x will be L do x star, right? X is your x star, L times x star, right? So L times x star. So similar thing will be common here, so we can take this as common. So this will be v star do u star by do y star. Okay, and over here this side, this will be g beta t minus t infinity is essentially ts minus t infinity, and then you will have t star. Okay, yeah, so and then this will be nu. From here you will have u naught, that will give you dou to u star by L square. Okay, L square, so that will be y star square. Okay, so this is what you get after non-dimensionalizing. Yeah, so you can rearrange further, and that will give you u star do u star by x x star, essentially this whole term here. Okay. So if you take it here, this will become g beta ts minus t infinity L by u naught square times t star, and this term, sorry, this term when you multiply here, this will become, you know, this will become your u naught L by nu, which is essentially 1 by REL star square. Okay, this is what you get after non-dimensionalizing your momentum equation. Similar exercise can be done for your energy balance equation. I'm not going to do the derivation again. Let's just write this as you know, we'll get u star dou t star by dou x star v star L. Then you of course have this dou t star by dou y star square. Okay, so this is what you get when you non-dimensionalize your momentum equation, and this is what you get when you do that for energy equation. Okay. Okay, so so far we have not defined u naught, right? We said that u naught will be some arbitrary velocity. Here, you know, in this case, if you look at the coefficient of t star, this is u naught square, and it is non-dimensionalized. So this does not have any dimension. This should not have any dimension either. So this term is u naught square. So this term has a dimension of u naught square. So we define u naught in a way that this coefficient becomes 1. If you do that, then your u naught is essentially u naught square is equal to g beta ts minus t infinity times L. G beta ts minus t infinity times L. Okay. So now if you look at the Reynolds number square, it will be, you know, u naught square L square. So this will become g beta ts minus t infinity L square L, and then you do L square. So this will become LQ, and then divide by mu square, right? So this we defined as what is known as Grashof number and Grashof L. Okay, so this is what is your, you know, kind of modified Reynolds number you can think of. You know, if you just write in terms of, you know, Reynolds number, it will give square root, etc. So to make it easy, you define what is you know, known as Grashof number, which is again you know, is function of you know, ratio, you know, which again is the ratio of your buoyancy, you know, because you have gravity and all those terms here, density and so on. This is buoyancy by viscosity. So your Reynolds number for forced convection was inertia by viscosity. So this again, you know, gives you comparison of buoyancy by viscosity. So you know, we'll look again in detail, depending on the relative magnitude of this buoyancy force versus your usual inertial force. You can define which mechanism, you know, convection mechanism is prominent, whether it's a natural convection or forced convection. Okay, so this we have done. So based on that discussion, you know, for forced convection, we see that our Nusselt number is actually function of Reynolds and Prandtl. Here we can say that our Nusselt number is actually function of Grashof number and Prandtl number. Okay, so you should note that this definition of Grashof number is actually independent of how do you know, essentially it actually comes from the definition of u naught, but it you know, it does not have anything. U naught is defined for with respect to Grashof number, not the other way around. Okay, so what we can from here, we have three scenario. Grashof number by, again, when you are comparing Grashof number, you have to compare with the Reynolds, Reynolds square, because that's how we define the Grashof number. So Grashof number and Reynolds number, if you compare, and if that ratio is close to 1, then both free and forced convection has to be considered. Okay. If your Grashof number is much smaller than Reynolds number, then your forced convection dominates. Here you should recall that actually this Reynolds number will be defined as VL by nu. Okay. If your Grashof by Reynolds L square is much greater than 1, then you have free convection, which will be the case if you have a stagnant media where Reynolds number velocity is very small. So Reynolds number is very small. So this ratio will be much greater than 1. Okay, so if this is the case, then your free convection dominates, and you can ignore the forced convection. Okay. So now that we have done the discussion, and we know that what should be your correlation should look like. We'll just look at some correlations for specific cases. So again, we haven't discussed about the numerical solution of this continuity momentum energy equation. In principle, it's possible to solve, and then it gives you Nusselt number, local Nusselt number for laminar free convection. It does not consider the turbulent. Even in free convection, you can have the turbulent flow, turbulent boundary flow in the boundary layer. We'll see a little later. Okay, one can integrate this, and so that your average Nusselt number, if you want to find to a certain distance L, it will be 4/3 times of Nusselt number at that location. Okay, right. So now this was equation for laminar flow. Now you could have a turbulent flow, right? You could have turbulent flow. So what will happen is as your boundary layer keeps increasing, then you may have somewhere you will have this instability, and then in these regions you will have, because it keeps growing, you will have turbulence. Okay, so you will have the eddies and all those things you can have. So such transition is known to occur at Rayleigh number. We are defining another this thing. Rayleigh number is defined as similar to what we did for Paclet number as Reynolds times Prandtl. Here we do Grashof times Prandtl. So that is your Rayleigh number. If Rayleigh number is greater than 10⁹, then you will have turbulent boundary layer. So this is Rayleigh number less than 10⁹. This is Rayleigh. Okay. Again, transition depends on relative magnitude of buoyancy and viscous forces. Similar to what we used to do in Reynolds number, where that used to depend on relative magnitude of inertial and viscous forces. Okay. So the empirical correlation by Churchill and Chu are given. This is for Nusselt number, which is 0.825, and then it depends on Rayleigh number, which is again function of it's essentially product of Grashof times Prandtl. And a relatively better accuracy may be obtained if you are in laminar region. This average this correlation for average Nusselt number is valid for entire Rayleigh number range. If you are in Rayleigh number less than 10⁹, then this correlation gives you better values. So the same these correlations can be also used for vertical cylinders. So we were looking at vertical plate. If you have a thin vertical cylinders, then you can sorry, not thin, rather rather thick, thick vertical cylinders, then you can use these correlations. So of course, by thick or thin, we have to specify D by L. So if D by L is greater than 35 by this, essentially what it means is that your boundary layer thickness is not too much. It's not is much smaller than the cylinder diameter. Okay, if that is the case, then you can use this correlation for the correlation that we just discussed. You can use that. Okay. Now we'll look at few more cases. Along horizontal cylinders also you can there are correlations available. So long horizontal cylinder essentially means that you have some hot cylinder like this, and then you will have some flow, etc. So if you look at the cross section, what will happen is you will have essentially the boundary layer formation. So because this is hot, so the density, the fluid that comes in contact with this horizontal cylinder will heat up and then rise, and then there will be a boundary layer formation, right? And boundary layer will grow. So as boundary layer, as boundary layer grows, what you can expect is actually Nusselt number actually goes down. So this is with theta, this is your local Nusselt number. Okay. Sorry for the bad drawing. So this is the case when you have TS is greater than T infinity. If TS is less than T infinity, then you can expect the reverse. Okay. Again, for this case, correlation is available, so you can find Nusselt number is 0.6 plus this, again the function of Rayleigh number, and then Rayleigh number is again depends on Grashof and Prandtl number. So Nusselt number is still the function of Grashof and Prandtl number. Okay, this correlation is valid if your Rayleigh number is less than 10⁻²². Similar correlation is also available for spheres, and then here you will see the familiar 2 plus thing. So if you're so this is 2 plus this. So even in the forced convection, we saw that if you have freely falling drop, you will have this. If your Reynolds number is very small, then this is actually 2. Okay, so similarly, for very very small Rayleigh number, this will reduce to 2. Okay. Yeah, so that's the set of correlations. There is not much to discuss. Only thing is you should be able to use these correlations and find essentially, once NU average, H average, and once H average, then from there Q. And all these correlations we did derive for fixed constant surface temperature conditions. There are some correlations available for constant surface heat flux as well, but the whole idea was to actually to give you idea why these correlations have this dependence on Rayleigh number and Prandtl number. And that actually you should appreciate that it actually comes from your discussion on the basic of flow equations and energy balance equations. Okay, so with that, let us do a simple practice question. So consider a glass shield of a fire pit. So in winter time you may have a fire pit at cold places. So you have a glass plate of 0.71 meter height and 1 meter width, and inside temperature of this you can again take the inside temperature as 232 Celsius. If the room temperature is 23 Celsius, estimate the convection heat flux from the glass shield. Okay, so we just discussed to find this heat flux, you have to first find H. To first find H, H average, you need to find NU average. And we just saw some correlations. There are multiple correlations available. So if you are given some different correlation, you should be able to use it. So you have to first find what is the appropriate correlation. In this case, you are given a correlation for this. So your job is essentially to calculate Rayleigh number, which is again Rayleigh number is product of Grashof and Prandtl number. And again, you should take properties at film temperature, which is Ts plus T infinity by 2. This is what we have done here, and you are given the properties at this temperature. So K, momentum diffusivity, thermal diffusivity, and Prandtl number. So now you just need to plug it in, but this gives you a way, procedure how to calculate actually heat flux. Okay, so you can spend a few minutes doing this problem. And with this, we conclude our discussion on convection. We looked at how to analyze convection problems. We looked at external convection. We forced convection and free convection. In forced convection, we looked at external flow, like flow over flat plate or flow past a cylinder and so on. And then we looked at internal flow, where we looked at flow through a tube, and we looked at how the temperature how much temperature drop or gain can be expected from inlet to outlet. And then we in this lecture we looked at the free convection or natural convection. In this case, we discussed how we introduced two new dimensionless number, namely the Grashof number and Rayleigh number, and you saw how Grashof number is in free convection is almost equivalent to Reynolds number in your forced convection. Okay, so with that, thank you. We'll have in next lecture we'll discuss radiation. So with that, thanks for your attention.